Harriet, a couple things. I went ahead and put this up here on the board, but just to clarify, so what I have here are the 3 leveling labs that we did, and what I did is I computed everyone's average misclosure. So this is the first leveling lab, the second leveling lab, and then the lab exam. And then, so remember, the misclosure is how far off you are from start to finish. So if you start at 100, you should end at 100, and you don't, there's error. So this is the average error per group, so I average by group. And if you can see, you're getting better. So that's good. I don't have the grade reports with me, and I don't have them posted yet to Blackboard. My goal is to distribute those in lab this week, so I just want to give you a heads up on that. Lab 6 will probably not be graded by, that's the resection lab, that will probably not be graded by this week because I have an exam in another class that I need to grade, so I kind of need to get that one done. Homework 4 was due today. How did that go?
Good.
That worked well? Was that difficult?
No. It's new. I didn't know what the word tabulate means. I had to Google it. Tabulate, whatever that word was.
Tabulate?
Whatever it was. I didn't know what it was. It was on there.
You just put it in a table.
What kind of table am I supposed to draw? Like no other papers. I don't know.
Did you get the right answer? I don't know which problem you're talking about. It started and ended at 0.
Last one. And it did start and end at 0.
Okay, then you probably did something right.
I didn't put it in a table.
I'm going to focus on this. Okay. I need to erase this because I'm going to use this space today in class. Okay. Today I want to, okay, so let's talk about logistics. Everybody pay attention up here. So we have the job fair on Wednesdays. This is what I'm going to do. I'm going to pre-record class for Wednesday so that you all can have time to go to the job fair. We're also going to start lab at 2:30 instead of 2 o'clock for both Wednesday and Thursday lab. We'll do the same thing in both groups, okay? What that means is we are doing that lab start to finish. I have done the lab handout that I've done. I think will make the calculations pretty straightforward, but we are doing it. The other thing that's worth mentioning is that we are doing the lab in Gullickson Field this week. So that's the one behind the between the tennis and the basketball arena. That's where the tennis courts and basketball arena. That's where we're doing the lab today. What I would say is for this lab, be there at 2:30 and be ready because I want to get started as soon as possible. Okay, sound fair? Okay. The other thing that's worth mentioning is that I'm assigning a homework today, but because of the nature of the topic, the homework itself isn't long, but it takes a little bit of time to explain. Given the nature of the topic, it is not going to be due until the 16th, which is 2 weeks from now. Okay? But the calculations are a little involved, so we're going to spend the next few lectures going through this. So the way this is going to work is today, we're going to go through some, what I would call, we're going to handle all the, I don't want to say confusing parts, but there's a couple things in the calculations that take a little bit of time to explain off to the side, things like terminology and angular adjustments and things like that. So we're going to do that part today. The pre-recorded lecture on Wednesday is going to go through the process of traverse adjustment start to finish. Then when we come back on Monday, we're going to have a full-blown start to finish in-class example so that you'll have something to go off of. And I think between all that, you'll see how it pieces together. And it's not really hard. It's just, it's a little involved and it's a little long. Okay? Everybody, so far so good? Okay. All right. So today, let's start talking about traverses. Everybody get the code? Okay. All right. So let's start talking about traverses. I want to make sure that we are clear as to what a traverse is, what we are trying to do in our traverse computations, and what we're trying to adjust. Okay, so let's talk about a traverse. All right, so what is a traverse? A traverse is a series of consecutive lines or consecutive segments, and each of these segments have the following properties. So I have here a 5-sided traverse here on the screen. Okay, so what I have, so here's what defines a traverse. So each of these points, these vertices, you'll hear me use the term turning points or just points or vertices. They all essentially mean the same thing. Each of those have been indicated and marked in the field. The lengths and directions of all of these segments have been determined from measurements in the field, and the line distances and angles between them are directly measured. Okay, so just a little bit of peering into the looking glass on how we perform a traverse. I might actually pull up those slides here in a little bit, because why not? Is that whenever we perform a traverse, we will perform an instrument setup on every turning point. Okay, and what we'll do, so like for example, if we're setting up on point A, we will point B, we will backside A and foresight C. So every distance on a traverse is measured twice, every internal angle is measured once. Okay, so when we start doing our calculations, we'll just take the average of those distances and use those for our adjustments. And I might pull up the lab slides just because I've got some nifty little animations that I hope work. Okay, traverses by their very nature should be closed, okay? And so, but I want to be clear on what I mean by closure. I don't necessarily mean that it has to start and end at the same point. So this would be what I would call a loop traverse, so it starts at A and ends at A, but this would be what I would call a link traverse, where it starts at A and ends at another point, we'll call it A2, okay? Both of these can be considered closed traverses as long as they start and end at points of known coordinates, okay? So a link traverse might start at one control point and end at another, and that is just fine in terms of closure, okay? What we are going to focus on are loop traverses, ones that start and end at the same point. The calculations are maybe a tad more straightforward to do. They're not any more difficult or any more complicated. Just the note keeping and whatnot's a little more straightforward if we're dealing with polygon or loop traverses. So that's what we're going to be focusing on here. But I want to be clear that closure does not mean that it actually starts and ends like in a loop. It just means that it starts and ends at points of known coordinates. Does that make sense? Okay. Now I want to be clear, whenever we do this in the field, we started this with the resection lab, but I want to be crystal clear on the process. When we observe traverse angles, we always observe them by turning to the right, okay? And so what that means is that when we're looking at a loop traverse, so if we start at A, we turn to B, and then B to C, C to D, etc. So if you look at the points, they are labeled in a counterclockwise fashion because of the way that we turn our angles, okay? So for example, you're set up at B, you turn to C, set up at C, turn to D, set up at D, turn to E, etc. So the points are labeled in a counterclockwise fashion, so we perform our survey in a counterclockwise fashion, okay? So whenever you're doing a traverse, it is conventional to survey around the loop in a counterclockwise rotation. Does that make sense? Okay, so I just mentioned that. These are the types of things, I don't want this part to be confusing when we start going into the calculations. I want this to just sort of be by instinct. Okay, we label the points counterclockwise. We do the survey counterclockwise. Okay. All right, let's talk about misclosure. I think we all agree that based off the experiences that we've had in lab so far, that there is going to be error present in your calculations or in your measurements. That's not going away. There's going to be error present, okay? For a loop traverse, theoretically what should happen is that you should start at A, work your way around, and end back at A. You're not going to, okay? That's not going to happen. What's going to happen is you're going to start at A, you're going to take your field measurements, and you're going to do all the math, and you're going to arrive at some new point. We'll call it A prime, okay? So there's going to be a difference between the starting and ending points. But I propose that with traverses, there are two different classifications. There's two different there's two different misclosures that we can have. The first is based off angular misclosure, which we're going to talk about today. Angular misclosure is a little bit harder to visualize, but it is present, and we're going to see today how it can present itself. But one's based on angular misclosure, one's based off linear misclosure. So this would be what I'm talking about with linear misclosure. I'm saying there's literally a linear distance between point A and point A prime. Theoretically, point A and point A prime should be the same point, but they're not going to be. There's going to be error present in the computations. Everybody with me so far? Okay. Let's talk about angular misclosure. Okay, so if I have a triangle, let's just think about triangles, for example. If I have a triangle, what are those three angles sum to?
180.
If I have a four-sided polygon, what are those angles sum to?
360.
What about five-sided?
540.
With me so far? Everybody get the pattern? The pattern specifically is that if you have a n-sided polygon, that the internal angles should sum to n minus 2 times 180, right? So if it's a three-sided polygon or a triangle, it's 180. If it's four-sided, it's 360, etc. We all know that's probably not going to happen in the real world, that there's going to be some error present. So I propose that the angular misclosure is the difference between the sum of the angles that you actually measure in the field versus what it should be. Okay, and it should be n minus 2 times 180. Okay. Now, if you remember, we could classify surveys based off of their elevation misclosure when we did levels. We can classify traverses based off their angular misclosure. And the calculation is very simple, or very similar. We have our misclosure equals some constant times the square root of the number of angles. Okay, don't worry, we're going to do an example of this here in a second. But similarly with previous surveys, we have an order and classification system which is based on the constant that we compute. When we were doing leveling, we were computing an M constant. Now we're computing a K constant. But one thing that's kind of nice, I will say, about angular misclosure is there's no issue in terms of, or there's less issue, I would say, in terms of units. The units are a lot easier to handle, if that makes any sense. We don't have to convert to millimeters and kilometers or anything like that. We're just going straight to the math. So far, so good? All right, let's do a quick, before we do the example, I want to mention angular misclosure and linear misclosure as well. Now, the way that we classify linear misclosure, do you remember when we did relative accuracy a while back on like homework 1, where we would do like so many parts of error per total measurement, right? Well, we're going to do the same thing with linear misclosure. And so what we'll do is we'll take this as our C value, that's the amount of linear misclosure, and then the distance traveled is just the length of all the segments. What I'll say is when you start getting into the swing of things of doing traverse computations, you'll see that this stuff is actually pretty easy to do. What I would say is if there's anything that I think is going to cause confusion in the calculations, this is not one of them. This is usually pretty straightforward. And then all we'll do is map that to our relative accuracy between points to classify the survey in that fashion. Okay. What I want to focus on, at least today, is the angular misclosure. Okay. The idea. So I have a six-sided polygon. Okay. And I have done measurements in the field, and I've measured these 6 angles. Let me pull this up on the notebook. Okay. So I've got these 6 angles that I've measured in the field, and I want to know what the angular misclosure is, and I want to classify the survey according to FGCS. Let me make this a little bigger. Okay. And I think you'll find this is pretty straightforward. Okay. So I'll give everybody a sec to write all this down, and then we'll get to chugging. Again, this is going to be pretty easy. Okay. All right, don't worry, I'll leave this up, and this is in our class notebook, so if you miss something, no big deal. Okay. So the first thing I want to do is I'm just going to straight up sum these angles. So to be clear, what we're talking about is we have sort of a 1, 2, 3, 4. Oops, I can do better at that. So we have this 6-sided traverse. Okay. I labeling this correctly? Am I? Which way are the labels going?
Well, those ones are going clockwise.
So did I label this correctly?
No.
No, exactly right. I'm making sure everybody pay attention. We label in a counterclockwise fashion, right? So we go B, C, D, E, F, right? Because at a given point, we turn to the right. We turn to the right. Turn to the right, okay? So what we've got is we've got 6 angles that we've measured in the field. So for example, angle A, this is 83, 31, 12. Angle B is 145, 47, 24. Okay, and so on and so forth. So let's just go ahead and sum these angles up. Tell me, when you sum these angles up, what do you get?
720, 0 minutes, 20 seconds.
720 degrees, 0 minutes, 20 seconds. Do I have a second on that?
Yeah.
Okay, all right. So this is what happens when you sum these angles up. Now what should they be?
720.
They should sum up to 720, right? So I'll put a little note here and I'll just say, you know, note sum should be. Now I'm getting frustrated because this pen is working just fine, and like an hour and a half ago it was driving me up the wall. Of course, as soon as I say that. So it should be n minus 2 times 180 degrees, or 6 minus 2 times 180 degrees, or 720. So that's like what it should be, but it's not. Now, based off what we've done in the field so far, is that a believable error?
Mm-hmm.
That's possible. That's very possible in the field. Okay. So what is our angular misclosure?
20 seconds.
20 seconds. So therefore, the angular misclosure is 720, 0, 20 minus 720 degrees, or 20 seconds. That's what the angular misclosure is, okay? So far so good? So if I wanted to classify the survey, so here's how I would classify it, okay? So what I would do is I would say, here, let's sketch a line out. I can do better than that. That's better. Okay, so what we're doing is we're using our governing expression that C equals K times the square root of N. Okay? And so C is going to be 20 seconds, and N is going to be 6 because it's 6 sides. Okay? So therefore, our K value is going to be C over the square root of N, which is 20 over the square root of 6. And what is that? .165 seconds. Do I have a second on that?
Yeah.
Okay. So what I can then do is I can go back to my classifications and I can say, okay, 8.165 seconds. Is that enough to be second order class 2?
Mm-hmm.
But is it good enough to be third order class 1? Yeah, so we are a third order class 1 survey. All right. So far, so good. So let me take a pause. How How is that? Is that easy to do? Any questions on that? Everybody good? Okay, so that part should be pretty easy, okay? So so now let's start talking about adjusting for these errors, okay? Okay, all right. So we've got these angles that we've measured in the field, and they do not add up to 720 degrees. But we agree they should, right? They should add up to 120 degrees. So how do we account for that? Okay. Well, first thing that we're going to do is we're going to compute an angular adjustment. Okay. So what we're doing in an angular adjustment calculation is we're assuming an equal distribution of error. Okay. And so what that essentially means is we're saying that every time we turn the instrument, we're assuming we can get an error. So we're going to assume an equal distribution of error. Okay? So what we do is we just take the angular adjustment as the total angular misclosure divided by the number of interior angles. So for the example that we just did, let me ask you a question. What would the adjustment be for this expression, or for this survey that we just did?
20 seconds.
No. The angular adjustment. So it's 20 seconds of error, but we had 6 turns. 3.33, right? Everybody with me on that? So, and I'm going to call it negative. So that's how much our adjustment is per turn. Okay? But the thing is, it's customary when we adjust our angles to round to the nearest second. So there's a little bit of a problem. If I take this and I round it to the nearest second, what would rounding this to the nearest second be?
-3.
Okay, now what's -3 times 6?
18.
18 is not 20, right? So how do we get that? How do we square that? There's a couple of different ways to do that. I'm going to show you the way that's probably preferred by most land surveyors because it is very Excel friendly. And the other thing I'll mention is that a second here and there is not going to desperately affect your calculation. So where you put that second correction isn't going to have a drastic difference on your final answer, but we do need to put it somewhere. Okay. So let me show you what we do. Okay. I'm going to kind of show you up here. Okay. So watch this. So I have an adjustment of 3.33 seconds. Okay. So what I'm going to do is I've got 6 angles. Okay, so the way I'm going to do this is I'm going to say, okay, let's do 1, 2, 3, 4, 5, 6. Okay, and what I'm going to do is I'm going to say, I'm going to multiply. Okay. All right. So let's see what we get when we do this. Okay. So 1 times this is just going to be -3.33. All right. 2 times this is going to be what? Like 6.66? Or 6.67? However you want it won't matter here in a second. You'll see what I mean. This times this, that's going to be 10. Right? Let's see if I know the pattern. That's going to be -13.33. That's going to be that. Is that fair? Okay. So now what I want to do is I want to round this to the nearest second. So this is going to be -3. This is going to be -7, -10. -13, -17, -20. Okay, so here's my angular adjustment, and that's how I'm getting from here to here. Is everybody okay with that? Okay, now this is the part that may be a little confusing, but once you walk through it, it's pretty easy. So what I'm going to do is I'm going to compute what I'm calling successive differences. And all I'm doing is I'm saying, okay, I'm going to start here. I'm going to copy this value over. Okay? And then here's what I do. To get from here to here, so everybody watch up here on the board. Okay? So to get from here to here, minus 4. To get from here to here, minus 3. Here to here, minus 3. Here to here, minus 4. Here to here, minus 3. You see what I did? So to get from here to here, minus 4. Here to here, minus 3. Here to here, minus 3. Here to here, minus 4. Here to here, minus 3. Here, I'll line these up a little better. Let's put this minus 3. About like that. I'll lower this down. Do you see what I did? It's very easy to set that up in Excel. Very easy. And if you sum this up, so sum this up, what do you get? You get 20 seconds. So they're all -3, but there's a couple that are a little higher. Okay? And so now what I will do here on the slide is I'll take those successive differences, and I'll add them over. So this first angle is 83, 31, 12. Add that, you get 83, 31, 9. Take this angle, 45, 27, 145, 47, 24, plus that gives you 145, 47, 20, right? And so I just add these up. Now I've got angles that sum up to 720. 720 even. Does that make sense? We're going to do that in some traverse computations later. And when you see those traverse computations and you see me do that, I didn't want that part to be confusing. Okay? So all I'm doing is I'm taking my adjustment, I'm doing multiples per step, and then doing these successive differences. Now, if it just so happened, like let's say instead of the error being 20 seconds, what if the error was 24 seconds? Well, 24 goes into 6 evenly, so I just had 4 seconds on each angle. So, make sense? All right, so is this good to go? Is this fair? All right, any questions? Okay. All right, now what I want to do is I want to talk about coordinates, okay? I want to talk about coordinates. I want to talk about some terminology. You've seen some of this terminology already in our last lab. Now I want to formalize it a little bit so that when you see these terms, oh, that's what was going on. That's what he was talking about. Okay? So first off, let's go to just basics. This is back to high school algebra. When we plot points, we need coordinates, right? X, comma, Y, right? Okay? In land surveying, we have a name for that. We call the X coordinate an easting. We call the Y coordinate a northing. Okay? So if you ever hear the term eastings and northings, sometimes you'll hear them flipped. You'll call them northings and eastings. What are northings and eastings? They're just coordinates. Just X, comma, Y. It's just our way of referring to that. Okay? Whenever we're doing a survey, it is common to initially assign an arbitrary coordinate to start out. So for example, we have a survey here. It's common to either assign your first turning point as an arbitrary coordinate like 5,000, 5,000, or maybe your control point as 5,000, 5,000. So if you remember in the resection lab that we did last week, we were using those control points, and one of those control points was 5,000, 5,000, right? So that was sort of common. We can also tie into a state plane coordinate system. We'll talk about that later. State plane coordinate system, short answer is there is a common XY coordinate system that we can use for a broader region in the state. We call it state plane because we have the various states in the country broken up into a series of planar regions. We can't use just a single coordinate system for the whole country because of the whole curvature of the earth thing. Okay, so when we've got these, so here's, for example, a four-sided traverse, and we've got coordinates for each of these turning points. And we call those coordinates northings and eastings, okay? So the question is, how do we get from one coordinate to another, okay? So how do we get, let's say, from turning point 2 to turning point 3? How do we do that? Well, if we're at turning point 2, there's two ways of thinking about it. The polar coordinate way of thinking about it is we go so far down at such orientation, r comma theta, right? But the Cartesian way of thinking about it is we go over so much in the x, so much in the y, right? So we have a name for that, for going so much along the x-axis and so much along the y-axis. And the name for that is a departure and a latitude, okay? So departures and latitudes are just, if you're at a given point, how much do you travel along the east-west direction and along the north-south direction to get to the next point, okay? So departures are your change in x, latitudes are your change in y, okay? So one question we got in lab was, can departures and latitudes be negative? Yeah, they can be negative because you're either going, for example, in the x direction, you're either going positive in the east direction or negative in the west direction. It doesn't matter, okay? Let me ask you a roundabout question. I want to see if you all are thinking about this. Let's say you have a traverse. Let's say you've got this four-sided traverse. So let's just think about the departures. If I were to sum up all the departures along the whole traverse, what should that sum be? It should be 0. Same thing with the latitudes, because think about it along the x-axis. So let's start at turning point 1. I go left some to get here, left some to get here, and then right some to get here, right some to get here. If I sum up all those departures, it should be 0. It won't, right? So you're going to do the same thing with the latitudes. You're going to get an error. Take the Pythagorean theorem, apply it to those sums, and by golly gosh gee, there's your linear misclosure. So there's a really straightforward way of doing that. Okay, so that's sort of the point I wanted to make. So yes, so departures and latitudes, of course, they can be positive and negative. Okay, make sense? Okay. So how do you compute departures and latitudes? Well, if you have a length and you have an azimuth, it's just sines and cosines. Now, some of you are going to think, wait, did you get this backwards? Shouldn't the x be associated with the cosine and the y be associated with the sine? That would be true if our angle was measured from the x-axis. It's not. When we report azimuths, we report azimuths from the y-axis turn. So those trig functions are flipped, okay? We take the x associated with the sine, the y associated with the cosine, okay? So that's why those are different, okay? Make sense? So when you see that later, I wanted to make sure that part was clear. So what do you need to get departures and latitudes from polar? You need a length. Now, where do we get the length? We can take the field measurements. Remember, we have 2 measurements for every length, 2 measurements. Take the average of that for our length, and the azimuth can be our azimuth computed in the field. We're going to have to compute azimuths, but we're going to do it using balanced angles. Don't worry, we're going to get some practice on this stuff here in a bit. Okay. Now, one thing we are also going to have to do is we're going to have to do the inverse. So if I give you a length and an azimuth, I want you to compute a departure and a latitude, but also if I give you a departure and a latitude, I want you to be able to compute a length and an azimuth. Now, if I give you a departure and a latitude, the length is pretty easy. It's just the Pythagorean theorem. But what about the azimuth? How do you get the azimuth from a departure and latitude? So, for example, if I start here and I go here, what's the azimuth from that line? If I just know delta x and delta y. Well, if you know delta x and delta y, you should be able to take an inverse tangent, right? And that's true, but we gotta be cognizant of signs, okay? So in quadrant 1, both of these terms are positive. In quadrant 2 and 3, the y term is negative, and in quadrant 4, the x term is negative. See, here's the thing. When you take the inverse tangent, you're ultimately taking the inverse tangent of a number, and that function isn't smart enough to know what quadrant you're in, okay? So what you're going to have to do is you're going to have to correct that, okay? So if you're computing an azimuth based off of delta x and delta y, if you want to know what that azimuth is, so if you want to know what the azimuth is, you take the inverse tangent of delta x over delta y. So you compute this, normally, but then you have to add a correction factor to that. Okay, and that correction factor is intended to help you figure out what quadrant it's in. See, if you take the arctangent and you plot it along the circle, see what happens is if you plot, okay, so this is 0, 15, 30, 45, 60, 75, 90. As soon as you cross this axis, this goes from positive 90 to negative 90. Well, if we would, for example, so let's say we've got this one right here. Let's say we've got this one. So if you take the inverse tangent for this line, you're going to get negative 45. But the azimuth is not negative 45, it's 135. How do you get 135? You add 180, okay? So if your coordinate is going to be in quadrant 2 or quadrant 3, you add 180. If it's in quadrant 4, you add 360, okay? And this part might be a little like, what? What are you talking about? That's why we have some examples. So let's do an example real quick. Okay, so let's say I have some points here. Let's compute some azimuths based on these points. Okay? Let's compute some azimuths based on delta x and delta y. There we go. Okay, so let's say I have point A and point B. So let's plot these on my little picture, my little graph here on the board. So 100, 100, that's going to be about right there. And 500, negative 200, going to be about like that, right? So our azimuth is going to run like that. So what quadrant is that azimuth going to be in? 2. So the azimuth should be between what two values? 90 and 180. Keep that in mind. Okay. So what we're going to do is we're going to compute let's compute a change in x. So which is positive 400. I'm leaving the decimals off because I'm just trying to get the concept to make sense. And we've got that, right? So before we start computing azimuths, I want somebody to help me out. What is the inverse tangent of delta x over delta y? It is the inverse tangent of positive 400 over negative 300. Okay? And just to make sure we're all on the same page, okay, I want to make sure we all know how to do this. Okay? So what we can do is we can say 400 divided by negative 300. Right? Here's that. Take the inverse tangent of that and say, watch this, okay? We take this, and if you hit that degrees, minutes, seconds button, it'll convert. So you just have to, that degrees, minutes, seconds button will automatically convert. So we go 53, 7, 48. But hold on, that's not what it said, okay? The answer here, this is what my calculator gives me. Negative 53 degrees, 7 minutes, 48 seconds. Okay, this is what my calculator gave me, but that's not the answer. What did we say the azimuth should be?
Between 90 and 180.
Between 90 and 180. That's where our correction factor comes from. We agree that this is in quadrant 2, so therefore, the azimuth for segment AB is 180 degrees minus 53, 7, 48, or 126, 52, 12. Now that is starting to sound like it makes sense, right? So that's what that correction factor is for, because ultimately you're just taking the inverse tangent of maybe a negative number or a positive number. The inverse tangent function is not smart enough to know what quadrant you're in. So if we wanted to do this next one, let's make sure we're all paying attention. So what is delta x going to be? What's that? Negative 800. What about delta y? 200. Okay, so here's what happened on this one. Okay, so what happened on this one is, all right, so here I'll erase this note because it's going to get in the way. Okay, so we started off at 200 comma 200, which is about right here, and ended up at negative 600, 400, so that's our azimuth. So that azimuth is going to be in quadrant 4, right? And it should be between 270 and 360. Now what this is going to mean is I'm going to take the inverse tangent of delta x over delta y, which is just going to be the inverse tangent of negative 4. And what is that? In degrees, minutes, seconds, by the way.
Negative 75, 57, 50.
But that's not our azimuth, right? And our azimuth is going to be taking this angle and doing what to it? What's our correction factor for quadrant 4? 360. So therefore our azimuth and that's going to be what?
284, 2, 10.
Does that make sense? Any questions? All right. In order to make our lab this week go a little faster, I want to show you a little bit about the process, okay? And so I think I'm going to run through my lab slides right now, because if we're starting lab late, let's go ahead and go through that. All right, any questions on that? Okay, so I've even got, I hope these little animations work. Okay. So what we're going to be doing in lab this week is we're going to be doing a 4-point traverse, and we're going to be doing it in Gullickson Field, the field outside Gullickson Hall. So this is Gullickson Hall, where the basketball arena is. This is behind that. We're going to be sort of doing it in this field, and this is the tennis court. That's where we're going to do it. So this lab's going to require us to walk a little bit more from this building over there. The first thing that we're going to do is a resection at turning point 1. Don't worry, the total station can do that automatically, so no more crazy calculations like last week. And then we're going to do a counterclockwise traverse setting up at each turning point. Okay, so I've got the coordinates for the Gullickson Field control points. I've got those in your lab handout. Because I'm letting you do the resection how you want, you can use any 4 of them. I don't care, or any 3 of them. Sorry, I'm giving you 4 control points. You can use any 3 of them. So there should be less people just sitting there at CP10 waiting. You know, now you can just use whichever ones you want. Okay, and I've got pictures. This is control point 20, 21, 22, and 23. We can go through that in lab, but I really want to go through the process of what you do in the field. Okay, so make sure that, again, I want to make sure we're clear on this. You're always setting your angle to 0 before you do an angular turn. Every time, and make sure you're always turning angles to the right. And in this lab, you're going to turn 4 angles inside the traverse as well as the additional ones at turning point 1. You're going to use all of them. So unlike the last one, you're going to use all of them. Direct measurements, you're gonna do all of them, but you're only gonna record the horizontal distances, because that's all you're gonna need for the traverse. Okay, so I wanna go through the steps, okay? So you're gonna start out setting up the instrument at turning point 1. You're gonna set up the instrument 4 times, 1, 2, 3, 4, so 4 different setups. And then for each setup, beyond turning point 1, you're gonna record 2 distances and 1 interior angle. So watch this. Okay, so here's the first step. So the first step is you set up at point 1 and you perform a resection. Okay, so you sight 4 or 3 of those nails, I don't care which ones, and you sight those 3 nails, and the total station will do that automatically. So you literally just write some coordinates, hit a little button, and it says the coordinates. All that, half hour of calculations that you did in the lab, there's just a little button that does it. So yeah. But now you know what it's doing, okay? And then the last thing that you're going to do is you're going to turn an exterior angle to the very last turning point, and then now it's time to take some measurements. So watch this. So we're still set up at turning point 1, take a back sight to turning point 4, turn an angle, foresight turning point 2, okay? So when it's all said and done, after you've done your setup at setup 1, this is what should be in your field book. At setup 1, you should have the height of the instrument, the height of the rod. You should have XY coordinates, XYZ coordinates for your first turning point, that exterior azimuth, and then here's what we've got here: a distance, an angle, a distance, distance, angle, distance. Okay. So then what you do is, now you set up at turning point 2, you don't need to do the resection anymore, so set up at turning point 2, backside, turn, foresight, okay? And then you got set up at turning point 3, backside, turn, foresight. Set up at turning point 4, backside, turn, foresight, okay? So every distance you've shot twice, every one, okay? So you can take the average of those when you're doing your computations for your traverse, okay? And so this is what your field notes should look like when it's all said and done. One thing we are going to do, we're not going to do it for the lab this week, because we're going to be sort of crunched for time. But for lab 8, I want so we're going to do another traverse. We're going to do one on Buskirk Field. For lab 8, I want every single person in this class to set up the instrument once by themselves. Everybody. Everybody. And I will take note of it. You are going to learn to do that. And so I'm going to make sure that now that we've got a few labs under our belt, we're all going to set up the instrument by ourselves. That's not this week, that's next week. I thought I'd throw that out there. Sound good? All right, this is what we're going to do in lab this week. I wanted to have you aware. All right, I'm going to pull up the code one more time for anybody who didn't get it, and I will see you all Wednesday or Thursday at 2:30.